Okay, next 45 minutes, I'm going to make an introduction and also some special issues related to the cold climate wastewater management, wastewater transport and wastewater treatment, the conventional systems. So at the end of this lecture, what I want you to remember is that in colder climates, especially the areas where we have in the northern cities, the distances are quite big, and the coverage area is also increasing per municipality, which also means that the wastewater transport costs are increasing. And the treatment efficiency is going down because of the reduction of temperature, the colder temperatures, and which means that to match the treatment efficiencies, the treatment costs are going up. So I'm going to show you some slides, some results to elaborate these facts. I'll start with the status in Norway. This is these are the different counties in Norway and how the treatment types are distributed. So the blue color means that the advanced wastewater treatment. So here the national average, like 60%, and the North Sea countries, North Sea areas, the average is here, and the rest of the counties, North Sea counties and the rest of the counties. This is the difference there's a big difference in Norwegian counties, how the treatment types are distributed. So in Oslo and the places we have a much higher percentage of advanced treatment, but when we go to the northern area, like Norrland, Troms and Finnmark, the advanced treatment percentage is quite low. And then we have the red part, that's the mechanical or in other simple treatment. The white or gray part is the portion of wastewater which is discharged without any treatment. And then we have the small treatment plants, like the ones that Pernille presented. So these are small treatment plants. Why there is no treatment in some places, it's also explained because of, although Norway is following quite rigorously European Union's wastewater directive, but when the population, the size of the treatment plant is less than 2,000, then the directive doesn't apply. And if it is under 10,000, then also there's no such, it's a less requirement compared with the big cities. So the result of this type of treatment or the lack of treatment is that the percentage of removal of phosphorus and nitrogen in North Norway is quite low. Then I will also take a slide from Tatiana's presentation, which shows what's happening in the population in the Arctic areas in the US and Canada. It's increasing in Arctic areas, but in Sweden, Finland, and Russia, yes, it's reducing. So this change of population has an impact on the wastewater management costs. This is because that when the population is increasing, the treatment plants which are built for one specific size, they cannot they cannot serve the increased population, which means that you have to invest in the expansion of your wastewater treatment plants. When the population is decreasing, sometimes the existing capacity might be sufficient. because if you think about the sedimentation tank, which is dimensioned for let's say 3 hours sedimentation, and if the population is reduced by 50%, then it suddenly has 6 hours of sedimentation time. So you get much better sedimentation. Of course, you will not be able to remove everything just by sedimentation, right? The other factor is that the treatment requirements are increasing in general. When the treatment requirements are increasing, then there is a need to upgrade, then it's a cost involved. Again, the cost of upgrading will be higher in colder regions than in warmer regions. Problems related to the cold areas are quite integrated also with the climate change impacts. It makes things worse or more complicated. And the climate change could have 4 main impacts for water supply and wastewater systems. The first one is the sea level rise. The second one is the heavy precipitation, more rain, more often, or it could be reduced precipitation, not in the case of northern, or at least not in Scandinavia, but some other places. And finally, also increased temperature. So how can they affect the water sector? When it comes to the drinking water part, the raw water sources could be affected because of the amount of water and pollution levels. Water supply infrastructure could be affected, distribution networks, if there's going to be a sea level rise, and the water treatment plants are affected, the processes are affected. So there will be some lectures later, I understand, on that. And the wastewater infrastructure, the collection networks, sewers, which I will talk a little bit now, and also wastewater treatment plants, the treatment processes will be affected. So cold climates and low wastewater temperatures. So there's I would say, a general understanding or a perception that the greatest challenge for wastewater treatment in cold climate regions is the low wastewater temperature. It's not so clearly correct. It's not so precisely correct because that the temperature and the very low temperatures occurs very occasionally, and especially in when the snow starts to melting. And the fact is that if we have less snow melting water leaking into our sewers, then the temperature of our wastewater is not going to be that cold as we think. So here is an example, an illustration explaining what's happening. So this is the temperature of wastewater temperature in a northern city during the 12 months. And the top curve shows the wastewater temperature in a sewer or a separated sewer. That means just the wastewater. But the red line shows the wastewater temperature in a combined sewer. Combined sewer means that it collects both wastewater and also the rainwater or snow melting water. So the problem is that most of our wastewater pipelines or the sewers in Norway, for example, they are still combined sewers. That means they collect both wastewater and the rainwater and snow melting, which means that is the reason that we get problem. That's why we get much lower temperature in our sewers, not because it's cold outside. Then another big issue related to our wastewater or the sewers is the floods. And this is a photo from Copenhagen from 2011. The capital of Denmark was flooded, and they have invested quite a lot. They have done a lot. After that, thought that it's not going to happen again, and 2014 it happened again. Right? And each time it's like, how much? It's 1.5 billion euros or something like that, the cost. Why is this happening? It's because so much rain, so much precipitation occurs in a very short time. So for example, like 330 millimeters of rain within 4 hours. It is impossible to have any sewer system to transport so much wastewater, so much rainwater within a short time. So you are going to have your city or your area flooded. And there are some predictions done based on the IPCC scenarios and systems. And here it shows that how the flood sequence, the mean floods will change compared from 1971 to 2000. And the first figure shows for the period of 2021 to 2050, and then up to 2100. So the dark blue ones means that the flood frequency is increasing, and the green ones are reducing. So you can see that, like in Bergen, the western coast, and also mid-Norway, and some parts of North Norway, there's going to be more flood. And it's not only a small change. So the circles are in this size means 40 to 60% of increase. So these cities are going to get much more floods, and of course much more precipitation, the reason for this. So when we get more precipitation, we will get, it's what I told you, that there will be increased risks of floods in urban areas. And when we get more rain, then, and also if we have combined sewers, we will have more water in our sewers. It will also result in that our treatment plants will be getting much more water because of this rain system, increased rain. Increased precipitation intensity and more rain in winters will increase the runoff and erosion because the ground is not becoming less permeable. Risk for overflows and pollution increase because when overflows occurs in a combined sewer, then you will get pollutants out to land. Increased discharges from the treatment plants because the treatment plants cannot cope with the increased volumes of wastewater. We have some treatment plants and where the wastewater volume could be 10 or 12 times more during a rain event. And we cannot afford to dimension a wastewater treatment plant to treat so much wastewater. We will also experience more frequent and bigger damaging floods in sewers. Then we are talking about our basements and other infrastructure. And sea level rise will lead to building up wastewater in the sewer network. So when we have more rain, more precipitation, and when it's going to happen more often and within a very short period, the problem is that there's going to be too much water in city or the roads, and we have too little capacities to transport the water out of our cities. So what can we do to solve this? The easiest and the simplest thought is that, okay, if the sewers are too small, why not build new sewers? But this is not that easy. If you take the Norwegian case, we can't even keep up with the normal rehabilitation needs. So The industry here has estimated that we need to renew our wastewater pipes at least by 2% every year. And the minimum expected is 1%, but the result is 0.6% per year. So that is just to rehabilitate the existing sewers. So how are we going to finance new sewers? So therefore, there are a number of other solutions coming up, like greener solutions. And one concept which is now tested, I think it's tested in a couple of places in Denmark and also in Norway, is to try to manage the sewers control based on the amount of wastewater coming, so that either you use retention tanks to keep some of the wastewater without sending it to the treatment plants, or that's the Danish solution. And in Norway, we are testing a concept whether we can use the reserve capacities in our sewers. Because if you take a city like Oslo, the whole sewer network is interconnected, and we can control our sewer pipes remotely. And when there is a rain event, the rain occurs only a part of the city, not the whole city gets the same amount of rain. So we can stop discharge from drier areas to our main sewers, and let the rain and let the sewers from the rain areas to get priority. So which means that some of the wastewater from drier areas will be collected or retained in the sewer. Thereby we are using that sewer capacity. So that's an example, but this type of solutions will not work in smaller cities or sparsely populated areas, which is typical for the northern Norway and Arctic areas. But for the bigger cities, yes. So I'm going to go into a little bit details on the wastewater treatment systems and technologies, how they are impact with the cold climate, and what kind of solutions we can find to deal with the challenges we are facing. Pernilla did a good introduction to the wastewater quality and also the basic treatment concept, primary, secondary, and tertiary. I would also like to quickly go through the systems in a different way, like mechanical, chemical, and biological processes. I'm sure most of you know details about these processes, but I'm also aware that some of you don't have this background. So in order to understand the rest of the lectures, I will use this time to go through the treatment processes. So the target in a wastewater treatment plant is to remove organic matter, which is coming from our toilets and from kitchens, remove phosphates, which is coming also from the same sources, and to remove nitrogen and particles. These are the four things that we are going to remove. So the basic system is called the mechanical treatment systems, as shown in this figure. First, you have a screen or sieve to take the most coarse particles. Then we have the grit removal, grit and sand, and then we have a settling tank. It could be 3 hours, 5 hours, just to let bigger particles settle. And then sometimes we have disinfection. So this type of a system can remove maybe 30–40% of particles, and which means that part of the organic matter and part of the phosphates, particulate part, will be removed. Then the next type of treatment is the biological wastewater treatment, where we get microorganisms to convert some of the pollutants to various different stages. Through that, we can remove some of the pollutants. For example, organic matter, where the organic carbon is, and we can make microorganisms to convert organic matter, organic carbon into carbon dioxide, and this is the basic process in biological wastewater treatment. Then we also need to remove phosphates and nitrogen. More advanced biological processes are there to do that. The third process is the chemical treatment, where we add special chemicals called coagulants. It could be aluminium based or iron based, sometimes calcium, sometimes polymers, where some of the colloids and smaller particles, they agglomerate and then they settle. So these are the three basic processes which you need to know to understand the rest of the processes and the challenges in the centralized wastewater management. In most cities, we don't have a single type of treatment. We don't have just mechanical treatment. In most cases, these are combined. So this figure shows a combination of chemical and biological and mechanical processes. The first one is called as simultaneous precipitation, and which means that the green part is the chemical coagulation. This one is the chemical part, and the red part is the biological part. So here the coagulant is added directly to the biological tank by activated sludge tank, and the precipitation or the coagulation and biological process takes place simultaneously. Then we have the pre-precipitation part. The coagulation chemical treatment takes place before the biology, and then the post-precipitation, where the biological process is first, and then we have the chemical process. So these are the three main combinations which we see in most treatment plants in Europe. Generally in Europe, or the continental Europe, they have built mechanical and biological treatment plants, but in Norway and some of the Scandinavian countries, we built mechanical chemical plants. But because in Norway, the target was to remove phosphates mainly, and in the continental Europe, the target was to remove organic matter and later on nitrogen. But because now, due to the European Union's urban wastewater directive, we have to remove both phosphates, nitrogen, and organic matter. We have to add, we have to supplement these processes, which means that most treatment plants in Northern Europe has all three processes combined now. And we also need to remove nitrogen and phosphorus, and especially the nitrogen removal. It is not so simple. You can't achieve it with a simple biological removal systems, biological treatment systems, and then you have to have advanced combination systems where both the anaerobic and aerobic systems are combined. So this figure shows the most advanced treatment processes what we have now. So that was a very quick introduction to the wastewater treatment processes. So if you cannot follow this, I suggest that you read on your own, because the rest of the material what we do here and discuss here, it will be dependent on your understanding of these processes. I don't know whether you have visited any of the treatment plants in Northern Europe or in Norway. Some of you who will be joining our next course next week, you'll be visiting a couple of plants. Most of the Norwegian wastewater treatment plants, they are fully covered which means that they are not covered artificially with roofs, but they are placed inside rocks. There are a number of advantages for this, because inside a rock, the air temperature is never below plus 5 degrees. So which means that there is no additional reduction of temperature of the wastewater because of the air temperatures going down. The other advantage is that there is no snow which comes or which dumps into our tanks. So if it is an open aqueous sludge treatment basin, imagine that you are going to get 1 meter of snow during one day, which happens sometime, or even half a meter. It's not that seldom. Then you are changing the temperature quite a lot. You are diluting your wastewater, and you can avoid these issues if you have your treatment plant inside rock. But when you have your treatment plant inside a rock, it means that you cannot just purchase the neighbor's land when you need to expand your treatment plant, if the population is increasing or if the treatment requirements are increasing. So this is the downside of having a treatment plant inside a rock, because it's going to be much, much more expensive to do expansions in such case. So we talked about impact of climate change, and then we are talking about the increase of temperature, the global warming, right? But now we are talking about the reduction of temperature in our wastewater. How this is happening? When the air temperature is going up, wastewater temperature is going down. Any suggestions? Yes, because the observations which we have seen is that the number of days where the temperature changes between around 0 plus minus degrees have increased a lot with the time, which means that snow, instead of staying for 3 months as snow, they start to melt almost every week, little bit around that. And when they smelt, then melting, then they will go into the sewers, because we have combined sewers, and thereby our temperature, or wastewater temperature, is going down. We have also observed that we are getting drier and warmer summers and wetter and warmer winters, which means that snow accumulation on the surface is reducing, and amount of sewer which is transported is increasing, and dilution of influence is also taking. Influence concentration is reducing. So in our treatment plants, we have higher volumes, lower sewer temperatures, and with lower concentrations. Lower concentrations also gives a challenge to most treatment plants, because if you take the Norwegian conditions, the discharge permits are based on the percentage of removal. So most treatment plants today have a requirement to remove phosphates, total phosphorus, more than 90%. Some has a requirement to remove more than 95%. So if the inlet concentration of total phosphorus is 5 milligram per liter, 90% reduction means that you have to remove 4, then your outlet concentration could be 1 milligram per liter. But if you have to remove 95%, if you have to remove 95%, then the outlet concentration is 0.5. But imagine if your inlet concentration is 1 milligram per liter of phosphorus, then you have to remove your phosphates levels below 0.1 or 0.5. because of the percentage concentration. So which means that when we have diluted wastewater, then we are facing challenges because the normal treatment systems will not be able to cope these type of requirements. When the temperature is changing or varying, how can we deal with this? The first and the basic rule is that we have to start using separate systems. The newer cities, there are a number of cities in China, I know that they don't have this problem because they have built their sewer systems in a way that they are separated from the beginning. They have one line for rainwater and one line for sewer, wastewater. In Scandinavian countries, the general practice is to, if we are building new sewers, then we try to build this as separate systems. The other solution is to select processes that can stand better variations in temperature. So this is the part that I would like to elaborate in my next slides and addressing some of the process techniques which can be used. Reduction of plant footprints, this is important not only in cold climates, but especially in cold climates, and also when your wastewater treatment plants are placed inside a rock, and also in urban settings. Urban settings, it is important to reduce the plant footprint because of urbanization, population is increasing, which means that you need to expand your treatment capacity. So one way to do this is to physically expand your treatment plant. That means that you can buy the neighbor's land and double the size of your treatment plant. But in most cities, this is not possible because the land prices are so high, and sometimes it's almost impossible to find any land for expansions. So the solution is that you need to find ways to make your existing treatment more compact so that you can build a new additional treatment in the same space. So we call it as the reduction of plant footprints. One of the best solutions which is used now is to start using the fine sieves. It means that a mechanical treatment, instead of using a sedimentation tank, we can have a filter cloth with a very small openings. Like 10-15 years ago, we have abandoned using these mechanical processes as the only process because the treatment efficiencies were so small. And we know that if the pore opening could be reduced to 0.1 millimeters, then almost 50% of the pollutants will be removed, particulate pollutants. But the problem is then the filter cloth will be clogged so often, and it is going to be very costly to operate. But now there are a couple of new technological solutions which are already in the market and installed, and they can have these filter sieves with so small openings as 0.5 to 0.1 microns. So it's this figure, it's a Norwegian Canadian company which has these belt sieves, and it is continuously running a filter, and it can remove more than 50% of total suspended solids and more than 20% of BOD. So if you install this type of system instead of a pre-sedimentation tank, then you will be reducing the need for the biological treatment system or the chemical treatment system coming after that by 50%. And then you can use that space to install an additional treatment process. Another aspect is to moving from activated sludge plants to more advanced biofilm processes. Here is an example from, I think it's from Manchester, for 1.5 million people. They were using huge area for activated sludge plants, and then it changed to an advanced biofilm process, and they could reduce the land by 75%. After the biological processes, we need to have a separation process to separate the dead microorganisms. So the normal process is to have a secondary sedimentation, so-called secondary sedimentation, which takes 2, 3, 4, 5 hours, because you just need to let all the particles to settle. But there's a process called membrane bioreactors. Instead of having a sedimentation process, we can put a membrane here. This is the sedimentation tank. This is the membrane process. So where you can reduce the separation time down to maybe half an hour, something like that. So thereby you can reduce the volume and area of sedimentation tank by maybe 5 times. Another process is ballasted coagulation processes. In normal coagulation, we have a flocculation stage. First the chemical mixing stage, then the flocculation stage, and then the separation stage, sedimentation. And sedimentation normally takes like 2-3 hours. But these so-called ballasted systems, which means that we add micro sand and the flocs grow around the sands, then the flocs will be sedimenting much faster. So this could be done also in combination with lamella sedimentation systems. And we have some examples which shows that the whole sedimentation process can be completed within 10 to 20 minutes. So if we have a treatment plant, let's say inside rock and in a cold area, and we need to increase our capacity and also increase our treatment efficiency, we can use this type of more intensive treatment processes, which will give more space and which will also increase the treatment efficiency. We could also use flotation, and there are special flotation systems. Flotation means that instead of letting particles settle down by gravity, you let particles go up. It's like when you open a bottle of Coca-Cola, that you will see that bubbles are going up, and if there are some particles, they will also go up. So this is the same process which happens in flotation. And if there are some efficient modern systems for flotation which can increase the efficiency by 70%, which can solve the capacity problems. So we are going to talk more about the chemical treatment processes, and there's a special reason for Norway to engage more about chemical treatment. And here you see the development of our treatment processes in Norway. So the green part is the mechanical percentage of mechanical treatment plants, or not the percentage, but the percent equivalence, but it's about 35%. And then we have the pure chemical treatment plants, chemical and mechanical, and then we have the biological and chemical biological processes. So at present, more than 70% of our wastewater is going through a coagulation process. And then it is important to understand what happens with the reduced temperature. When the temperature is going down, what could be the impacts? As Pernilla said, that when the temperature is going down, it gets more viscose. When the water is more viscose, then the settling process gets retarded. If we have a biological wastewater treatment plant and we see that it's not functioning well enough, the capacity is low, the treatment process is not good enough, and you don't have a space and you need to make things more efficient, a good solution is to install a chemical process before the biological process. So as this figure shows, so in a biological treatment process, about 30% of your organic matter will be taken out during the pre-sedimentation, and the biological process itself has to remove about 60%, and the 10% is going out. But if you have a this pre-sedimentation, if you convert it to a coagulation stage, then it will remove about 75%, maybe 60 to 75% of organic matter. Then the biological plant needs to remove only 15% of the organic matter. And chemical treatment plants are much more compact compared with the biological processes. That's why when you introduce a chemical precipitation plant here, you can get a net increase of the treatment capacity of treatment plant. So there is not everywhere that you will find coagulation and biology is combined, but there are both advantages and disadvantages with coagulation. So the biggest advantage is that coagulation is often not dependent on temperature, or it's not so dependent or so influenced by temperature effects as in biological processes. Chemical processes can remove phosphates and suspended solids remarkably. That we have seen also Pernilla's experiments showing that the phosphates were removed down below. Almost all phosphates were gone after chemical treatment. And it's relatively easy to control, and low footprint and low energy consumption. But this is debatable because it's low energy consumption inside the treatment plant, because in a chemical process, chemical coagulation process, you don't have to add energy. But in a biological process, you have to add energy continuously to make the conversion of organic carbon into carbon dioxide. So chemicals are needed. You have to purchase chemicals all the time. Biological or organic matter removal is limited. It can't remove, chemical processes cannot remove dissolved organic matter, and it also produces more sludge and poor settling at lower temperatures. Because of the viscosity, and it's also the floc building intensity is also reducing in lower temperatures. Organic matter removal efficiencies are debatable with chemical coagulation, but here is a table showing what the experience from Norwegian treatment plants. And as you see here, these treatment plants show removal of over 70% of organic matter. And this is because that when we have chemical coagulation, we can remove quite well particles. The suspended solids in the outlet could be less than 10 milligram per liter. So this is one of the reasons that we can remove quite a lot of organic matter. So how does the temperature impact on coagulation? Floc formation during wastewater coagulation is known to be slower at lower temperatures. And sedimentation, when the flocs are developing slower, which means that the floc size is smaller, and then the sedimentation and filtration, flotation processes could be negatively influenced. So, which means that you need to have bigger sedimentation tanks, and you might also need to have more chemicals. It's going to get, by that way, it's going to get more expensive, more costly in building your treatment plant and also in operation your treatment plant. So I'm going to conclude here now before to break for the lunch. And the conclusion from here is that today we have mostly combined treatment processes, and the chemical processes could be affected by lower temperatures, and we get lower temperature in wastewater because of the air temperatures increasing, and which leads to snow melting more often, and then more rains lead to increased wastewater volumes in our sewers, and also creates problems in our cities related to floods, and floods also lead to increased pollution to the water resources of our cities. Right. So I'm going to break here now, and then we will continue after lunch the rest of the lectures. Thanks.